Okay. My name is Minjan. I will be the instructor for the USACO Gold class, of course, as well as the bronze and silver and also platinum class. A little bit of my background. By training, I am a mathematician and also a mathematician and also computer scientist. And in the past 20 plus years, I've been working on algorithm development and also implementation. Worked in the biomedical field and also worked in the financial field. So I had experience working with big data. So in the financial world, a lot of data, stock trading, option trading, commodities trading. In biomedical field, with genomic data, proteomic data, and also image data. So in each category, there are plenty of the databases that need to be analyzed, to be processed, to find out the information that may be useful to guide the operation afterwards. Okay, so let me share my screen here. For the earlier today, for the bronze and silver, I talked about the arrays, how to access, how to traverse the elements in an array, one-dimensional, two-dimensional, how to use them. The reason I also told earlier, right, would be it is hard to explain a topic that I need more time to warm you up. So the same holds for gold. So I'm going to talk about a type of the algorithm, the greedy algorithm. So sometimes you don't need very fancy data structure or very fancy idea implementation. Greedy by name, right? You're going to just try. Maybe you cannot convince yourself, say this, or can prove this is the right solution, or this is the maximum value, this is the minimum value. I cannot prove it, but my intuition tells me, yeah, I should go this way, or I can find the right solution, go in this direction. Many times this will work. Well, if you have time, right, then why not try it? If it works, then do it. Later, you can finish the proof. This may also hold true in the real USACO contest. Within the 4 hours or even 5 hours, sometimes you just cannot afford to prove your theorem or a series of theorems. So just go ahead with the heuristic or with the intuition and then say, let me run it. And of course, right, based on your prior or previous experience, you believe there is a high probability that you're going to succeed. Or say, if there are 10 cases, maybe I don't need to solve all 10 of them, but if I can solve, get the right answers for the 8 or 9 out of the 10 cases, I'll be happy too. And many times, here I want to point out, right? Many times if you read the code from other people, read the solution from the USACO website or other websites, looks like the answer is so beautiful, so elegant. But actually, all those, well, not all of them, but many times, right, the solution has been polished afterwards. Nobody can guarantee during the contest, you're going to find a beautiful idea and implement it and then try to polish it. No, you don't have to. This is also the experience, right? Not just yourself, pretty much everybody, right? Once you submit your code and you see, right, all of the cases have passed, you're going to move on to the next problem, right? So you don't want to say, okay, I want to reduce the number of the lines from 89 to 74. I know many students have the urge, right? I want to make sure my code looks beautiful. That's okay, that's actually a very good thing, but you do that after the test. Of course, right, in the everyday practice training, well, first solve it and then don't stop there. You go one extra mile, and many times that build up the accumulation will make huge difference in 6 months, in 1 year, in 2 years. So, okay, a little bit on the philosophy. So during the test, try to find a solution as fast as you can. You don't have to make it perfect, right? 1,000 points will make you pass, get you promoted, but 900 will also make you promoted. Maybe not the same round, but you will be getting promoted next round. Of course, right? You say, I finished the questions, even though I did not get perfect score, but I still have 30 minutes left. By all means, right? Keep working on them and always save a copy or tell yourself, right, which submission passed the most cases. So later, if you say, I made some changes, the number of cases passed, right, dropped from 9 to 7. Well, in the last minute before the time expires, right, go back and resubmit the version that passed 9 cases, right? So we'll just keep a note or anywhere, right, on a piece of paper or on a note to yourself. Okay, so with this, I'm going to talk about, illustrate 2 questions today using greedy algorithms. Normally, the greedy algorithms, right, it does not guarantee it will be the optimal solution global, in the global sense, but it holds the property, right? It is the best solution or optimal solution locally, or with the information I've seen so far, I cannot find a better solution, or I believe this is the right way to go, then try for it. But again, I want to emphasize, right, after the thinking, either you pass all the cases or sometimes, right, if you don't pass all the cases, right, then you're going to think about it. If it passes, right, why it works, or if it does not, then why it does not work. Okay, so here is one example. This one is cards average. Okay, so I have this file here, the description. Also, I have the file that is at the Google Drive. Actually, from the announcement, right, all of you should have the Google Drive address. So for the purpose of self-containment, right, I'm going to post this address here. So if you don't have it, you can click on it. And then actually the files I write in class will be uploaded to the Google Drive. And also there are 2 assignments also have been uploaded there. All right, so the question says, there are n piles of cards with A1, A2, all the way to AN. The sum of all the cards is a multiple of n. Then we can talk about the average. And we're going to define a move. It's defined to be, you can move any cards, any number of cards from pile K, either to pile K minus 1 that is on the left, or to pile K plus 1 that is on the right. Of course, right, you cannot move more cards than pile K has. For example, right, pile K has 5 cards. You cannot move 6 cards to the left or to the right. So only move cards that is currently available at pile K. So this is defined as one move. And of course, right, at pile 1, you can only move to pile 2 on the right. And at pile n, you can only move to the left, that is pile n minus 1. All right, so we have defined the moves, we have defined the array of integers. Now we need to report the minimum number of moves so that after that, all piles have the same number of cards. That is, every pile has the average. This is possible because we have assumed the sum is a multiple of n. So this is possible. And we're going to assume n is at most 100,000 and each pile has at most 1 million cards. Actually, this one does not matter. You can make it a billion, which is okay. Now the input, first line has n, the number of cards, and the number of piles, and then each of the next n lines specifies the integer a j, where j goes from 1 to n. And output is just one number, the minimum number of the moves, so that every pile has the average number of cards. Okay, so here is one example, the sample case. Sample, there are 3 piles. Of course, this one is easy. So 3 piles, pile 1 has 5 cards, pile 2 has, oops, down here. I mean here. Pile 1 has 5 cards, pile 2 has 4, and pile 3 has 3 cards here. The answer is 2, so we need at least 2 moves. Since the sum is 12, so average would be 4. We cannot move this way here because this will go from pile 1 to pile 3. That's not allowed. So we can do this, right? Move 1 card from pile 1 to pile 2, so that's 1 move. And then we're going to move 1 card from pile 2 to pile 3. So that's 1 move here, that's another move here. So total 2 moves that will work. So in general, how do we find out the minimum number of moves so that eventually all piles would have the average? Okay, don't think about the fancy structures, as I said, right? I picked those questions because we don't need them. Meaning we're going to find out a greedy algorithm. Okay, I'll pause a little bit here, and so you have time. Sweep left to right. That is a good idea. Alex has a very good idea. Actually, based on what Alex said, right? I can sweep from left to right. I can also sweep from the right to left. Very good. Very good idea. Okay. McKinney also has the idea if there are piles to the left. That's also a good observation. So if I have a pile here on the left, less than the average, right? I can find out the average when I read the input, right? So I do have the average. So if a pile here, right, this one is less than the average. So say this is negative, less than the average, right? I should, well, somehow, if I say add the numbers here, right? Okay, maybe I have something here. So up to this point, if this one, well, maybe up to this position J that I am considering, if the sum is negative, and I have to move cards from the right to this right of position J, right, to position J. I mean, overall, I need to move cards from right to left. But if I just look at this one position, can I say I have to move cards from right to position J? Or maybe I have more cards from the left. I can do this. That's fine too. All right, so here, actually Alex's idea is a very good one. So do you want to elaborate more, Alex? Yeah, you can talk, that's fine. You don't have to type. Okay, look at here. I am moved cards from the left to right. Okay, Tom's idea, can't you just move cards from the left to right? If they don't match, well, right, what if my cards are like this, right? Then I cannot move cards from the left to right. Tom's idea, George, take and add cards to the right. I agree, but not exactly what I'm thinking. Fix some in each pile. Okay, Ben's idea, right? Want to do, I think you mean a partial sum, kind of, right? Okay, Alice's suggestion, move cards from the biggest to the smallest. Okay, also very good idea, but okay, so if I do have, like this is like the mountain, the number of cards, right? So it's right, I know this is probably the first reaction to many people. I want to, so suppose that's the average. So I'm gonna move, right? This pile has too many extra cards, so I need to move them away. But how many do you want to move to the left, and how many do you want to move to the right? Yeah, Nathan's idea, right? We're gonna find out the average. So for each one, actually, I can assume, I can change the input rather than have A1, A2 through AN. I can find out this B array. So BJ is actually AJ minus the average. So this is actually the difference from AJ to the average. So if you add them together, right? If you add BJ here, we should get back to 0, right? Okay, so working with array A or working with array B actually would be equivalent. You're right, our idea, our purpose is to make every element in BJ to be 0 by doing the move. So a move in array A and a move in array B would be equivalent. Okay, so all you have done, have talked about actually all good ideas. Okay, we need to move, right? So here, well, we do have the restrictions, right? You can only move, say here, you don't want to move too many cards here. You don't want to move too many cards so that if this one becomes too small, that's not necessary, right? So we're gonna find out the minimum number of the moves. Looks like this is a hard question. How do you find out the minimum count of the moves? That's true. So for BJ, some of them will be negative, right? If the sum of BJ is 0, some of them is positive, then some of them must be negative. That's true. Okay, Raymond has an observation, right? Each move can either make the situation better or worse. Of course, we don't want to make it worse. Of course, right? How do you define being better or worse? So maybe I can define the more elements in BJ being 0, that is better. Alex, you're right. You can move multiple cards. As long as you don't go say, here there are 10 cards, right? You cannot say, I'm going to move 11 cards out of this pile. That's not allowed. But besides that one, you can move any number up to the number of cards in that pile. Okay, so let me change this viewpoint a little bit. I know the difficulty here many times, right? If I do have a big pole here, right? Sometimes you do have to move some cards to the left, some cards to the right. The extreme case, right? This one is the biggest, all the others are 0. The extreme case, right, you see, all n cards are at this location here, and all other places, right, are 0. So some of them would be moved to the left, some of them would be moved to the right. Okay, yeah, of course, right? When this question is designed, right, you know, some extreme situations will be like that. Okay, then, well, this one I just give you the extreme case, right? Maybe there are A spots here. Here you have B spots, right? Then you have to move A cards from this pile to the left, move B cards from the pile to the right. Okay, suppose I have another pole. This will make life a little bit hard, right? So here, there are 2 poles. The others are very small or 0. Then you have to make sure, right? Don't put too many to the left, because you have to make sure there will be enough to the right from this pole. Okay, so I want to go back to a comment Alex made at the beginning. Okay, the question, can you count how many cards would be needed on each side? Okay, that's a good question, actually. That also, it's the idea that Alex mentioned at the beginning. Nathan's observation also fine. So at every location here, not in here. So at a position J, I want to find out how many, what is total on the left, what is the total on the right. So if there are more cards on the left, then you write, overall, I need to move cards to the right. So on the right, so this would be J minus 1 times average. So that's supposed to be the total number of cards that I need, right, for the left-hand side to be in good shape. So if the left-hand side, right, the total sum is less than this one here, then I now have to shift cards, I have to move cards from the right to the left. And if this number is bigger than this J minus 1 times average, then I have to move cards from left to right. Okay, so now let me go. Okay, so Ben's idea, right? Find the first position where the prefix average is bigger than average. Okay, so all these are good ideas, but I'm going to say change the viewpoint. Go back to what Alex said at the beginning, which I think will make life much easier. So I'll give you the hint, right? What Alex said was you can move cars positive or negative. Remember, right? Alex said we're going to sweep from the left to the right. But if you sweep from the left, what do you mean, right? So here you have 3 cars, 4 cars here. You cannot move cars from the pile of 3 cars to the pile with 4 cars. Now, AZ, I'm not sure whether your formula is right. Oh, let me see here. Oh, an lowercase n is the variable. Okay, I'm sorry. Didn't see that one. Is that still correct? You're right. Okay, Alex, the idea. Okay, let me go back to what I just said right here. So I cannot move from pile 3 to pile, the pile 1 to pile 2 here, right? But I can move cards from pile 2 to pile 1. Okay, if I have 5, 4, 3, that makes sense, right? I'm going to say move 1 card from pile 1. You can see the motion of my pen, right? Okay, so I can move 1 card from here to here. That's fine. I can move 1 card. But this one, I want to say I want to move -1 card from pile 1 to pile 2. Does it make sense? I move a negative number of cards from pile 1 to pile 2. Yes! Why? That is the same to say I'm going to move 1 card from pile 2 to pile 1. Okay, if you have this idea, then life becomes much easier. Tom, I think you got the idea, yeah. Very good. Okay, so do you see what I'm trying to do here, right? So at this point, when j is, well, actually, say j is 1 here, 3 is less than average. Actually, the difference is -1. So say I'm going to move this -1 from left, from position 1 to position 2. So this count as 1 move. So this one, since minus -1, so this becomes 4. This becomes -3. Now this will be 3 here. 4 plus -1. 3 minus -1 is 4. This one accepts the number of cards from this pile 1, right? Accepts -1, so this becomes 3. Now at this point, right, this one is less than the average, so I'm going to move -1 from this pile to this pile. So after this move, this becomes 4. This also becomes 4. Then I'm done. So this will be the second move. Okay, very good idea. So if we have say 1, 1, 7, right? So average would be 3. So here I'm going to add -2. So this would be 3, -2, this would be -1 here, right? That's one move. And another move, this will make it say -1 minus 3, this will be -4. So this would be 3, and then this -4, that's 3. The second move here. You're right. You don't need the order here. You only need the number of moves, right? Past a little bit here, right? You say you cannot move -3 from here to here, right? You don't have it enough, but the opposite always is true. You say if this one does not have does not have enough, right? Negative, then that means you have to wait until this one comes, moves more cards from the right, put it here. Okay, pause a little bit, think about it, why this makes sense. Exactly, Amy's idea is right. All right, so this is a greedy algorithm, right? At every spot, J here, to make this one optimal, I'll just say, by force, I'm going to make this one the average. So if it has more than enough, move it to the right. If it's less than enough, I'm going to drag it from the neighbor to my right. Yes. Now, the answer would be easy, right? Actually, from what we just described, what is the complexity for this idea? Very good idea. So this one actually is big O-N. Yay, very good, right? Okay, so as I said earlier, in USACO training, this is our philosophy or our belief. From the beginning to silver level, we're going to just use Java because Java is used in schools for computer science classes. Actually, not just for high schools, for most universities, so far computer science is still taught in Java because it is perfect for the OOP, object-oriented programming. Now Python is getting in, actually starting from 2019, the number of people using Python actually has overtaken the number of the people using Java. Popularity of machine learning. Since machine learning, most people started using Python. The reason is say Python was a scripting language, so it is easier to do check it. It will take less number of lines to write the idea. That's why it is popular. The same as when I was working in say financial data, I would do the prototyping in MATLAB because it is more powerful. So many times you need to write a a procedure or func class in Java. I have to write maybe say 50 lines, 100 lines, but in MATLAB, maybe just 5 lines. That would be enough to go. So due to that reason, Python has been popular among people doing the machine learning AI. But Python was not a compiled language, was still scripting, and also was not OOP. But now Python is trying to migrate into the family of OOP. Maybe in the next 5 years, if Python can successfully migrate to the family, then I'm pretty sure the most popular language, the truly popular language, would be Python. There's not, there's no other reason to say people like it, and then people, then more people will have to use it. So we cannot say, right, Java actually is better than C++. Well, there's some features Java is better. For example, right, C++, you still have the pointer. And from my experience, and also a lot of people's nightmare, the pointers are just giving you headache. Okay, for small projects, that's fine. But for big projects, the pointers are just troublemaker. So Java does not allow that one. So every time if you want to access an element, a position in an array, in a vector, in a list, right, it will check the boundary for you. So there's no way you can go out of the bound. Java, I mean C++ does not. Okay, but for most experienced programmers, right? Well, the boundary checking, I can do that. That's not an issue. Yeah, so depends. Okay, so in the Gold class here and also Platinum class, we're going to do both C++ and Java. Python still not recommended because Python so far the speed is still not fast enough. Even though if you submit your solution in Java and Python, both would be allowed 4 seconds, but sometimes 4 seconds are just not enough for Python. So no matter how hard you try to optimize to make it better, you just cannot finish the calculation within 4 seconds. But Java is okay. Every problem, you know for sure. Well, if you do well, right? If you optimize, if you be careful enough, you should finish every question in Java. But there are cases, right? Python cannot finish. So you can also see from the past statistics, the number of the Python users still would be just a fraction of the Java and C++. All right, so here I'm going to give the solution in both C++ and Java. Okay, so let me work on this question here. So I'm going to clear this part here. So I'll just write this part here, and you can see this is the average. Cards. I think this one is just cards. So I'm just do cards here. So import java.util.star. And I'm not sure what IDEs do you use. I use Eclipse. It is a light-weighted IDE. That means it is rather small. Actually, I noticed it's no longer that small. I liked a lot at the beginning. I just updated the current version, that is June 2020. Okay, this one, if you check the memory, it takes, Eclipse actually takes 500, actually it's getting better. When I just loaded, it takes about 1 gigabytes, which I don't like it. Now it's dropped to 500 megabytes. That's much better, okay? Used to be much smaller. Eclipse, if you run it, say 2 years ago or 3 years ago, it takes about 200 megabytes. That's kind of neat. And then another one that I've used a lot for Java programming was NetBeans. NetBeans, it does contain the GUI part, the graphics user interface, but we don't need the graphics at all, right? So why bother to upload that part that takes the space in memory and make it running slow? So my preference is Eclipse. Also, of course, right, this depends on the project. If you do a big project, especially graphics, maybe you want to do NetBeans. Okay, so here, suppose I'm gonna do buffered reader. Yeah, equals buffered reader. Come on, file reader. And this would be say cards.in, and I need to exception here. And I'm going to put this one to the print writer. PW print writer. First, I'm going to read the n. What is the format for this one here? I'm going to read n first. br.read9. So this would be the number of piles. And I'm going to have this one, right? So array A equals new. Is it int? Since I'm going to put it, I'm going to make it this long. And string tokenizer. What? Stop doing this one here. String tokenizer st equals new string tokenizer br.read9, and j goes from 0, j less than n, comma, and aj should be integer dot pass nt. This one should be passed along. st dot next token. Next. Why does okay, so I'm done with this one here. I'm going to say pw dot close vr dot close there, and I need to find out the average. So long average is 0, and average plus equals aj here, and average should be divided by n here. All right, so we're going to sweep from left to right here. So j goes from 0, j less than actually n minus 1 here, because the last one should be, once you make sure n minus 2, that pile is working, then pile n minus 1 must work. And the total moves. Actually, this would be the, okay, I'll just do the count. This would be the number of the moves I need if aj is not equal to average. So aj plus 1 should be increased by aj minus average, and count increased by 1. At the end, pw.println count, then I'm done. Right, this is the idea, what we just discussed. If this pile, right, is not equal to the average, if it's positive, then we're going to move the number of cards from pile j to j plus 1. If aj has less than average, I'm going to move a negative number. That means I'm going to move more cards from the right side of j to pile j. All right, so this is the code. So not hard to implement, right? So this idea move from the left to right, but may move. So we may move a negative number of cards from j to j plus 1. Once you have this idea, then the question becomes easy. Well, let me change, right? Will become easier. So if you take the question from the first glance, right, the first idea, it may be hard. Turns out this one is easy. Using this idea, this greedy algorithm, and it works. Okay, and if you want to do the, I do have the C++ version. Okay, so here, called average. Oh, by the way, I use dev C++. And roughly the same idea. So move, I have updated the average here. So if this one is actually the B array, right? If B is not 0, move B to B plus 1, BI plus 1. So the same idea. Okay, so this would be easy to go. Okay, again, right, this one does not have any of the fancy structures. Just find the right move. In this case, it's not move. Have a good observation, see what you can simplify the process. As Amy pointed out right here, we don't, and also several others point out, right, we don't actually care about the order. So if at power j, the number becomes negative, don't worry. That means you have to wait for the sum of the powers on the right to move cards to the power here. So, okay, another idea, another example I want to show here is the card game. Well, the reason I put this one here because that's a card. This is also a card. Card game, December 2015 Q1. So let me take a look at this question here. Oh, by the way, this IOI this year has been postponed, and very likely this will be canceled this year, since the pandemic is not getting better yet worldwide. Actually, it's getting worse. So, okay, this one is easier to define or characterize. Is it getting better or getting worse, right? If the total number of people get affected, if it's getting higher and higher, then it's getting worse. Otherwise, it's better. Or if you say, right, the number of deaths is getting down, that's better. Otherwise, it's worse. Okay, so the question here, the card game, high card wins. Okay, I'm not sure whether you have worked on this question before. This is a typical one. If you want to classify or categorize for each problem into, say, the topics, you know, right? Maybe divide and conquer, maybe some structures, maybe say minimal spanning tree, maybe shortest path, and so on. I'm going to cover in the class later. For this one, actually, it does not fall into those categories. So, in my opinion, this one is best classified as greedy algorithms. Okay, so here, the question, if you have not done this before, I'm going to explain. There are two players, Bessie and Elsie, and we'll be given the cards for Elsie here. So we know the order of the cards that Elsie will play. This N is the number of cards for each player. So Elsie has 4 cards. The number will go from 1 to twice of N. This is the N here. So the rest of the cards would be Bessie, player 1's hand. And then N is even. The rule says in the first half, so 1, 8, 4, 3 here. And then for Bessie, the cards will be the rest, right? So this would be 2, 5, 6, and 7. Okay, so player 1, 2, 5, 6, and 7. The first half, N is even here. The first half, whoever has a big value will win. In the second half, whoever has a smaller value will win. So in the first half, whoever has a big number, right, will win. If I do this right, this will be 1 win. The second half, whoever has a smaller value will win. But in this case, right, Bessie has big numbers, so the win here would be 0. So I don't want to play Bessie's cards this way. Rather, I'm going to do this. I'm going to put 6 and 7 here, right? Since big numbers win, so I should put big numbers in the first half for Bessie. Okay, you cannot change the cards for Elsie, but you can change the cards for Bessie. All right, and then we're going to put the small numbers in the second half. So 2, 5 would be put here. So I still have 1 win here, but I have 1 win here. 6 is bigger than 1. So the first half I have 1 win, 2 less than 4, so I have another win. So here we have 2 total wins. So the answer is 2. All right, so for this question, kind of, in a sense, similar to the card's average problem. Very good idea. This is actually a very good observation or a good heuristic, right? So in the first half, to beat player 2, this is P2, that's P1, right? To beat P2, don't waste the resource, right? I'm going to find the first card that is bigger than this one and then use this one to beat here. Of course, right, this one, 8, I don't have any card to beat it, so I'll just say give up. Okay, so, okay, this is the idea. Actually, I did mention or say one thing, right? You cannot change player 2's cards or the order of the cards played by player 2. But I need to retract this sentence. Actually, we can. No, William, that's a good idea. You're right. When I say I can change the order of P2's hands is in the first half, I should be able to sort it. In the second half, I should be able to sort it too. Do you agree? Right? In the first half, Bessie knows what cards to be, will be played by Elsie. So if I can change my order, right, that means I can change the order of P2's cards. You're right. Okay, so this is a greedy algorithm. So we're gonna read the cards for P2 from the input, and then we're going to decide the cards for P1. Again, P1's cards, right, will also be split into 2 halves. So we're going to take the big cards, the big half of player 1's cards play in the first half, and then the smaller cards, the smaller half of the cards, right, will be played in the second half here. Because first half, big cards will win, and the second half, smaller cards will win. And then for each half here, we're going to sort P2, sort, of course, right, P1's cards already been sorted. When I say, right, P1's cards have been sorted, think about it one way, right? This is a good exercise. When I say, right, I read P2's cards, then I can find out the P1's cards sorted. Okay, I'm going to build an array of size 2n. So when the card of P2 is met, I'm going to mark this one to be, say, true here, true here, true here, and true here, right? And then for those places not marked as true, right, as false, that will be the cards for P1. I'm going to read them one by one. So this one is an array of size 2n. So this will take big O n time to process P1's hand. And when you read them, they will be sorted already. Anyway, you can do other ways. Still n log n, that's still fine. Even though they're not sorted at the beginning, right, you can still sort, that's not a big deal. But anyway, there is an easier way to find out the P1's cards sorted. Okay, now I'm going to take the second half, play first. For the first half, actually play the second part. Okay, and then we're going to sort P2's cards in the first half. And then we're going to do one by one here. So for each card here, P2, find out the first card in P1 that can beat it. And then we're going to move to the next one. So this one, actually, if you want, this one can also be placed under the category of indexing. This one is double indexing. So there is index I here, there is index J here. So this is P1, this is P2. For each J here, find out the first I so that P1I is bigger than P2J and then increase J and increase I. What if P1I is less than P2J? Let J stay here, increase or advance I. If I reaches the end or if J reaches the end, then we know we have finished the loop here. And of course, right, I would always reach the end faster than, no later than the J goes to the end here. Okay, and the second half, you're gonna do the smaller one. Again, two indices, right, I and J here. This time, if P1I is less than P2J, that's good. Both indices will advance. But if P1 is bigger, let me see the other way. I'm going to focus on I here. For each P1I, let J move. If P1I is less than P2J, both will advance. If P1I is bigger, then just increase J. So this time J would reach the end sooner than I reaches the end. Actually, both will reach the end n over 2, right? Half of the cards, so n over 2 here. And then you just do the count 1 here, count 2 here. That's the count in the first half, count in the second half. Add them together. That's the number, the maximum number of the rounds that P1 can win against P2. Okay, so again, for this question, the first glance may scare you a little bit. Say, what can I do to find out the max value, the max number of the wins player 1 can have? Okay, from the heuristic, right? If I want, in the first half, right, if I say P1 wants to beat P2, do you want to use a number that is too big to beat P2J? No, you want to find the smallest number here in P1 so that it can beat P2. So using the heuristic, then this becomes, again, easy, right? So the double indexing, we're going to use 2 indices to index the 2 arrays. The complexity for this one is big O n over 2, and this one the same, big O n over 2. So together, this one is still big O n. So a question that seems to be kind of complicated, very likely should go even more than n squared, right? If you want to do some brute forcing, that would be exponential. Turns out this one can be solved in big O n time. Oh, actually, I will take it back. If you want to sort P2 in the first half, sort P2 in the second half, that still takes n log n. I'm sorry, take back, right? The overall complexity, it's n log n, but except the sorting of P2's hands, everything else should be big O n. You're right. The double indexing, it's a process used in the merge sort. Right. Okay, good. So again, I will upload the solution both in Java and in C++, and you can take a look. If you have solved this question before, perfect. Actually, this is the first problem since USACO has changed from the 3 layers, bronze, silver, gold, to the 4 layers, 4 divisions, bronze, silver, gold, and platinum. So this was actually the first problem. And I still remember, right, many students took this test and said, wow, it was much easier than before. And actually it was. Okay, that is true for season 2016, 2017, and then after 2018, 19, things got a little bit back and it's getting harder. And I'm pretty sure, right, 5 years, in 10 years, this contest will be more competitive. Why? Because more students, hardworking students used to spend more effort in USACO Math Olympiad, Physics Olympiad. Now find, yeah, okay, this USACO is more interesting. And actually, maybe it's more applicable for my future job and career. So, and I've heard many people talking about big data, the, you know, very competitive programming, have a huge amount of the computations to be finished within a short period of time. So this is good. Actually, it is. Okay. So the purpose, right? If some of you attended the sessions this afternoon, I mentioned this, right? The purpose for the class, especially gold class and then platinum class, the goal is not just say to get a trophy, to help you with your college application process. Actually, the goal, we're going to look further. So in 10 years, 20 years, that's the era for you guys, right? That's the explosion of big data. So who can understand the question, who can come up with good ideas and then implement and also explain them clearly to sell your idea, to sell your products, that will be the winners.